like, I mean, besides the harmonic, and now there's like just a little number there.
But it's not like I had you figure out by adding each term before.
Well, that would be really cool. That is possible. So.
Yeah. Okay. So now this weekend, when you're out Friday and Saturday night with your friends, you can impress all them and say, I can add up this infinite series just equals square root 3 over 2. Okay.
All my friends are in like math 22 or 26.
Actually, how long?
Okay, thanks. Questions so far? Okay, so let's deal with this next one now. So what series does this one look like? Harmonic as a factorial. Right, e to the x. Yeah, so be careful, harmonic doesn't have a factorial. So e to the x is a sum from 0 to infinity of x to the n over n factorial. And so now, okay, this looks similar to the Maclaurin series for e to the x, except here our exponent is n minus 1, and here our exponent is n. Okay, so we want to change the exponent here to n, so we're going to do that by splitting up the exponents, and I have a sum. I have n plus negative 1, so how do I split it up? I multiply, right? So this becomes a sum from n equals 0 to infinity of negative 1 to the n times negative 1 to the negative 1 over n factorial. And what is negative 1 to the negative 1? Or just negative 1, because that's just 1 over negative 1, right? So if this is negative 1, I'm just going to bring this outside. So I have negative of the series from n equals 0 to infinity. Because this is negative 1, it's just a constant. I can bring that outside. And then I have negative 1 to the n over n factorial. Okay, and so let's just write out the first few terms just for kicks here. Okay, so if I plug in n equals 0, I get negative 1. If I plug in n equals 2, if I plug in n equals 1, I get positive 1. If I plug in n equals 2, I get minus 1 over 2 factorial. So it just be 1 over 1 factorial. And if I plug in n equals 3, I get plus 1 over 3 factorial, and so on. And again, this goes on forever, so how am I going to find a sum of an infinite amount of terms? Well, I'm just going to use this Maclaurin series, okay? This is now of the form of e to the x, where x equals what? Right, negative 1. In the form of e to the x, where x equals negative 1. Okay, just this part after the negative sign. Yes?
So do these always have to be in the form
of one of the Maclaurin series, yes. Mm-hmm. Any other questions? So now I have negative, and now it's still the form e to the x, where x equals negative 1, so I just plug negative 1 in for x. Okay, so I have negative e to the negative 1. And that is negative 1 over e. Any questions so far? Bless you. So now we're asked to find the sum of this series, okay? And so here we're given term by term, we're not given it in summation notation. So now what we need to do is express it in summation notation. Okay, and then we can see which Maclaurin series this is similar to. Okay, so first of all, what do we notice about all our exponents and factorials? Right, they're even. So all exponents and factorials even, so express as 2 times n, right? Because 2n is divisible by 2, so therefore it's even. Okay, and so now we're going to find the pattern here. So we write it in summation notation. I'm not going to write the index yet. Let's just save that for later. Okay, so first of all, 3, pi, and 4 are all raised to the same exponent, right? 3, pi, and 4 are all raised to the 2 here. 3, pi, and 4 are all raised to the 4 here, and so on. Okay, so I can write 3 pi over 4 raised to the 2n. Again, I want to raise it to the 2n because all my exponents are even. Let me move that over. Okay, and so in the denominator, I have a factorial. Okay, again, that factorial matches the exponent, so that should be the same thing since they're all even. So I have 2n factorial. And so if I'm going to write this, what does my index need to start with? Right, it needs to start with 1, because now when I plug in n equals 1, my exponent is 2, and the first term, my exponent is 2. If I had started the index at 0, then my exponent would be 0, but that doesn't match the first term. Okay? All right, so one last thing I'm missing. Alternating, so how do I express that? -1 to what power? N, okay? So always check here, if I plug in n equals 1, I get -1 to the 1, that's negative, and my first term is negative, so that's correct. It should be 1 to 1. Okay? So which Maclaurin series does this look like? Right, cosine. So here's the Maclaurin series for cosine. Okay? So can I just say that this series equals cosine of 3 pi over 4? Why not? Right, good, because the index does not match up. This index starts at 1. Okay? Looks like cosine x, but first we need to change lower index to n equals 1. Okay? So n equals 0. If you guys are awake. So we need to change the index to n equals 0 so that it matches up with the Maclaurin series, right? So now I'm going to go ahead and change the lower index to 0. So I have the sum from n equals 0 to infinity, -1 to the n, times 3 pi over 4 to the 2n over 2n factorial. Okay? And so here my index starts at 1. Here my index starts at 0, so I cannot say that these are equal because they're not, right? And so the only difference between these two series is that this one contains an extra term, namely when n equals 0, because here my sum starts at when n equals 0, and then it goes to n equals 1. Here it just starts with n equals 1. So again, this contains an extra term when n equals 0. Okay, so here if I have an extra term when n equals 0, what do I need to do to make these equal? Right, I subtract, because here I have an extra term. right? I have an extra term, which is n equals 0. Now I need to subtract it in order for it to equal this summation, because this one is missing that n equals 0 term. So I